Hello, future engineers, subscribers, viewers, and students. Here is another video in beautiful and challenge problems in calculus. I know that for some or many, these problems are not challenging or not beautiful, but for those who are learning calculus their first time, these problems are good representatives to challenge the minds of those who want to become engineers in the future. So these problems will be discussed on the next slides. So the first problem, suppose that 2 joules of work is needed to stretch a spring from its natural length of 30 centimeters to a length of 42 centimeters. How much work is needed to stretch the spring from 35 centimeters to 40 centimeters? Then B, how far beyond its natural length will a force of 30 newtons keep the spring stretched? So for part B, after we solve the spring constant, we used Hooke's law to solve for 31B. For 31A, work is equal to K over 2, spring constant over 2 times quantity final displacement square minus initial displacement square, where final displacement is the difference between the final length of the spring and its natural length. Then the initial displacement is also final length minus initial natural length. So that's the idea. So work is K over 2 S square minus SI square. And the geometric interpretation of this, don't forget the area of the force versus displacement curve between SI and S and under the force versus displacement curve. So 2 joules is equal to K over 2. Quantity S is equal to final length 42, initial length 30, so 12 cm, and 12 cm is 0.12 meter, while SI is 0 because it is stretched, the spring is stretched from its natural length. So 30 minus 30 is also 0. So substitute 2 joules equals K over 2 quantity 0.12 square minus 0 square. So solving for K is 2,500 newtons per meter. Then we can now answer 31A. Work is equal to 1 half of 2,500 over 9 times quantity. The final displacement, if the spring is stretched from 35 to 40, is 40 minus 30, so 0.10 or 0.1. Then SI is 35 minus 30, 0.05. So work is 2,500 over 9 divided by 2. Quantity 0.1 square minus 0.05 square. So it is 1.042 Newton meter or 1.042 joules. For B, force is Ks by Hooke's law, and K has been solved. So F is uh, 30 newtons. K is 25 over 9. Then, since the question is how far beyond its natural length will a force of 30 newtons keep the spring stretched? So since it begins with the natural length, S is the stretching beyond the natural length, and SI is 0. So 30 equals to 500 over 9, quantity S minus 0. So S is equal to 0.108 meter, or in cm, that's 10.8 centimeters. Then we proceed to 31B. A spring has a natural length of 20 centimeters. Compare the work WK1 done in stretching the spring from 20 to 30 with the work WK2 done in stretching the spring from 30 to 40 centimeters. How are WK2 and WK1 related? So work is equal to this So work 1 is equal to, so since the natural length is 20, so S is 0.1, 30 minus 20, 10 cm or 0.1, SI is 0. So it is 1/2 of K quantity 0.1 square minus 0 square, and that is work 1 is K over 200. Work 2 is K over 2 quantity. So from 30 to 40, so that means S is 40 minus 20, 0.20 cm or zero point 0.2 meter, while 30 minus 20 is 0.1 meter, 10 centimeters or zero point 0.1 meter. So S is zero point 0.2 meter and SI is zero point 0.1 meter for this problem. So the work 2 is K over 2 quantity 0.2 square minus 0.1 square. Simplifying, that is equal to 3K over 200. Since K over 200 is work 1, we say that work 2 is the work done by the force in the spring in stretching it from 30 to 40 is 3 times that of the work done by the force in stretching the spring from its natural length to 30 cm. So work 2 is 3 times work 1. So that's the answer. You just divide this by that or replace K over 200 by WK1. Then problem 31C, if 6 joules of work is needed to stretch a spring from 10 centimeters to 12 centimeters, and another 10 joules is needed to stretch it from 12 cm to 14 cm, what is the natural length of the spring? So I will express the work done by the force in the spring in Newton centimeters instead, and I'll let X be the natural length of the spring. So 6 joules times 100 cm, 6 Newton meter times 100 cm, so this is 600 Newton centimeters equals K over 2 quantity. So it is, the spring is stretched from 10 to 12. So final displacement would be 12 minus x, 12 minus natural length, quantity square minus initial would be 10, this one 10 minus x quantity square. Simplifying, 1200 equals k times quantity 144 minus 24x plus x squared minus 100 plus 20x minus x squared. Simplifying further, 1200 equals k times quantity 44 minus 4x, call that equation 1. Then 10 joules is needed to stretch it from 12 cm to 14 cm. So 10 times 100 equals k over 2. Quantity final displacement is 14 minus x, initial 12 minus x. So 1000, 10 times 100 equals k over 2 times quantity 14 minus x squared minus quantity 12 minus x squared. Simplifying, that's 2000 equals k times quantity 196 minus 28x plus x squared minus 144 minus 144, then plus 24x, then minus x squared. Simplifying further, 2000 equals k times 52 minus 4x, call that equation 2. So to solve for x, we divide equation 2 by equation 1. So we have 2000 divided by 1200, that's 5/3. So we eliminate k, then equate it to 52 minus 4x all over 44 minus 4x. Cross multiply, 220 minus 20x equals 156 minus 12x. From here, we can now solve x. 220 minus 156, that's 64 divided by 20 minus 12, 8. 64 over 8 is 8 centimeters. So the natural length of the spring is 8 centimeters.